second family of reactions that we're going to look at in this unit are those that are actually opposites to synthesis, and they are called decomposition reactions. So, like in the first video in synthesis, we're going to use a sort of a people analogy also to introduce this notion of decomposition. And grade 11s, you have quite a number of different types of decompositions to be able to predict products for, whereas grade 12s, we simply have to recognize what a decomposition reaction looks like and be able to identify one as such as opposed to predicting products. So in decomposition reactions, we have a number of scenarios. Our first scenario is a situation where we have two non-metals bonded together in a molecular compound. And what we can do in this molecular compound is we can decompose it back into its original non-metal elements. And these non-metal elements would have no charge on them. They would be perfectly neutral. The second scenario that we have is this case where you have an ionic compound. And in an ionic compound, we would have to take this solid and we'd have to heat up to a crazy temperature in order to break it apart, but it could be done. And what would happen essentially is the electron that the metal had given to the non-metal would go back from the non-metal to the metal, and we would end up with a metal element and a non-metal element. And again, these would be elements and they would be in their neutral states, not their ionic states. The next scenario that we have is an ionic compound that happens to be a hydrated ionic compound. So it has some number of water molecules attached to it, which I'll just leave as the value of x, where x can be 1 through 10. You'll notice in this equation that I have an arrow with a triangle underneath it, and that triangle is meant to represent some type of heat source. You could even think of it just as a Bunsen burner flame to remember that. Now the neat thing about water, of course, is that it changes state from liquid to gas quite easily, and we can remove the water from this ionic compound easily just through heating it. So that we end up with, after heating, the ionic portion of that hydrated compound and the waters coming off as steam. And so what would be left behind would just be the ionic solid in the container that's holding these hydrated crystals. The next three are specific to 3U students. We can take three families of ionic compounds, those that contain chlorate, those that contain carbonate, and those that contain nitrate. And in similar fashion to the hydrated ionic compounds above, we can heat them up. And they do decompose in a very predictable manner. The first one decomposes into the metal part of that chlorate compound bonded with chloride. Okay, and that would be a solid that would be left over as well because it's ionic. It would have a very, very high melting point. And a gas would be given off, and that gas in this case is oxygen gas. In the case of carbonates, we can heat them up to quite high temperatures too, and the metal cation that was with the carbonate would bond this time with oxide to create some sort of ionic compound left behind in the reaction container. And in this case, the gas that gets given off is carbon dioxide. And then finally, if we take nitrates and we heat them up, although I wouldn't recommend it because they're also very strong oxidizers as well, but they can decompose as well in a very predictable fashion in that the cation part of nitrate combines ionically with nitrite, there we go, NO2, 1 minus, to create some sort of ionic compound. And once again, the gas that's given off would be oxygen gas. So the neat thing to note is that they're very, very predictable. The gases that are given off here always occur for those specific ionic compounds that contain complex ions. And this anion here, here, and here is always predictable and always comes from the left side of the equation. And of course the cation stays the same and keeps its charge as well. So let's dive into some examples of looking at these sort of different decomposition families. So again, as I mentioned at the beginning, decomposition is the opposite of synthesis, where we have one compound breaks down or decomposes into two or more elements, or they could be smaller compounds as well. So our first example is a molecular compound. We have hydrogen chloride produces hydrogen and chlorine as our word equation. And we can translate that into a chemical equation. Hydrogen chloride would just be H plus H and Cl right there. And hydrogen and chlorine are two of the Hofbrinkel, or the group of 7 elements in the periodic table that must be always written as diatomics. And you can see clearly there they are in their neutral states because they are elements. We could also show how this reaction works through pictures instead of just words. And so we could create an HCl molecule like we would with the molecular model kits, and an H2 and a Cl2 as shown. But the interesting thing here is that it doesn't decompose in a 1:1:1 ratio. We can see that in this equation, there's one chlorine on the left and 2 on the right. And so in order to balance them, I would need to clone that reactant molecule to have 2 of them. Of course, in the essence of cloning it, we also end up with 2 hydrogens on the left, which already have 2 hydrogens on the right. So it would take 2 of these HCl's to decompose at a time to create an H2 and a Cl2. Let's look at the breakdown of a hydrated ionic compound. So again, we have one reactant on the left. In this case, it happens to be barium hydroxide octahydrate, and we can put the little bullet in there to show those 2 portions of that compound. And as we said earlier, if we heat that up, the water comes off and it leaves behind the ionic piece. And so this one is a really nice one because it's actually a true split. In that just the ionic piece stays off by itself unchanged, and the water gets heated up as steam, and there would of course be 8 of them because there were 8 to start with, and you just have the water evaporating, leaving the solid behind. Now for the grade 11s, let's take a look at what some of these decompositions with chlorate, carbonate, and nitrate might look like, just so that you have some examples as well. So again, if we go back, remember that chlorates decompose into something with chloride, and we get some oxygen gas. And that something is going to be the metal portion of this compound, or the cation. And so we can put K plus with that Cl, and we get oxygen gas on the other side. And we could take some time to balance that equation as well. I notice that the potassium and chlorides are already balanced, but the oxygens are not. There's 3 on the left and 2 on the right. So we're going to have to multiply those up to the lowest common denominator, which would be 6, which means we have to double this one, and we would have to triple this one to balance the oxygens. But doubling the reactant means that the potassium and the chlorides doubled as well, so we would have to double the KCl on this side as well. And as I said earlier, this would be an ionic solid. These starting reactants would also be solids because they too are ionic compounds, and ionic compounds are solids at room temperature. Let's look at the carbonate example. We said earlier that carbonates like to decompose into something that combines with oxide, and that carbon dioxide is given off. And so this will end up being an ionic solid. Let's put the cation with it. The cation that's featured in this particular compound is sodium. And over here we needed 2 sodiums to balance out the charge with carbonate, but let's see what happens here on the right hand side. Well, sodium has a 1 plus that happens to combine with oxygen, happens to be a 2 minus, so we are going to have to require 2 sodiums in that formula also to make it balanced by charge. And lo and behold, if you do this one by inspection quickly, you'll see that it is in fact balanced. There's 2 sodiums, 1 carbon, and 3 oxygens on both sides of the equation. Let's do one more example. Let's look at the nitrate example too. So calcium nitrate decomposes, as we heard earlier, into some sort of cation that bonds with the nitrite, and oxygen gas is given off. So let's go back and examine what is the cation. Well, it's calcium. So let's put calcium with nitrite. And we can see that from a charge perspective, they're not equal. We're going to need 2 of those nitrites in order to balance the charges within that new ionic compound. And lo and behold, if we go back and double check to see if the equation is balanced, it is in fact balanced the way that it is in a 1 to 1 to 1 ratio. So in summary, decomposition reactions are very easy to identify by inspection because you will always see just one reactant on the left-hand side. And on the right-hand side, from the examples that we saw in this video, we had 2 products, but there are also reactions that have much, much larger reactant molecules that can break down into many other smaller pieces as well. They won't be the focus of our study because they don't follow predictable regular patterns, but we would have 2 or more products on the right-hand side.